Imagine, like, trying to estimate the GDP of a city,
Okay.
but a city you've never even visited, and you're just looking at a satellite photo of its streetlights.
Yeah, that sounds impossible.
Right. But for years, AI developers actually thought, bright lights just automatically meant rich cities.
Oh, absolutely. They relied heavily on that.
And the models would look at, like, a neon-soaked tourist trap with 0 permanent residents
Right.
and completely hallucinate a booming local economy.
Yeah, they saw a symptom and they just assumed the disease. It's really a fundamental flaw in how artificial intelligence has traditionally tried to understand the physical world,
Exactly.
especially when it comes to the complex, highly contradictory spaces that we call cities.
Which makes the mission for today's deep dive incredibly relevant for you listening right now.
Oh, definitely.
We are unpacking a state-of-the-art Gen AI paper. It's an August 2026 release titled Multi-Agent Collaborative Reasoning with Tool-Augmented Evidence for Urban Region Profiling.
It's quite a mouthful.
It is. But, this isn't just about tweaking some old algorithm. This is really laying the foundation for the future of urban computing.
Yeah, and we're working from a stack of highly technical sources today, all centered around this breakthrough framework called UrbanAgent.
UrbanAgent, right.
Right. Researchers from the Hong Kong University of Science and Technology, the University of Washington, and a few others introduced this for the KDD 2026 conference.
Awesome.
And the core challenge they are tackling is urban region profiling.
Right, which is basically this seemingly impossible task of estimating a city block's carbon emissions or GDP or population distribution.
Without having to physically knock on every single door.
Exactly. Or install a million sensors everywhere.
Yeah.
So whether you are an urban planner or a tech enthusiast or just insanely curious about how AI is decoding the very streets you walk on,
Yeah.
this deep dive is going to completely change how you view the concept of smart cities.
Well, to really appreciate the new solution, I think we first have to look at the mechanical failure of the previous systems.
Yeah, let's establish why the old way is totally broken.
Right. So traditional deep learning approaches this problem through what's called multimodal representation learning.
Okay.
Because cities generate a staggering amount of heterogeneous data, right? And each type of data tells a very different story.
Yeah, like satellite imagery provides a top-down physical layout, showing where the roofs, roads, and green spaces actually are.
Exactly. And then textual descriptions scrape the web for municipal zoning laws or even social media reviews.
Right, right. And then points of interest, or POIs, they map out the exact GPS coordinates of cafes, banks, logistics hubs, all that stuff.
And don't forget the 3D building models. They give you volume and height, which is crucial for differentiating, say, a sprawling one-story warehouse from a 50-story residential tower.
Right, so we have all these completely different types of data.
Exactly. And those are fundamentally different languages. I mean, an array of pixels from a satellite versus a spreadsheet of business licenses versus a 3D geometric mesh.
That's a lot.
But the traditional models don't even try to read them side by side.
Wait, really? They do?
No, they take all those completely different signals and they mathematically mash them together into a single latent embedding.
Oh, wow.
They force the data into a unified vector, attempting to find a mathematical consensus, regardless of whether the underlying facts actually agree.
Okay, let's unpack this because that sounds crazy. So if the problem is that we are forcing text, satellite, and business data into one confused mathematical space,
Right.
it's basically like tossing wildly different ingredients into a blender.
That's a perfect analogy, actually.
Like if your satellite image shows a quiet, low-density neighborhood filled with trees, but your text data says it's an emerging commercial district,
Yes.
the blender just makes a confusing, gray, contradictory sludge.
Yeah.
The nuances are just destroyed.
Exactly. And the AI just spits out whatever the statistical average is, hiding all the contradictions.
Wow.
The researchers actually call the result of that blender approach the correlation-driven fallacy.
Correlation-driven fallacy. Okay.
Because the model has, pureed all the context away, it can only rely on the most superficial patterns it memorized during its initial training.
It's just pattern matching.
Right. It has no causal understanding of why a city functions the way it actually does.
Which brings us back to that neon lights hallucination we talked about.
Precisely.
The model learns this brittle rule, right? Like tall buildings plus bright lights equals high GDP.
Yeah.
So when it encounters a massive hotel district in a city it hasn't seen before, it just applies that rule blindly.
Exactly. It completely misses causal factors, things like local economic policy, taxation structures, or the actual function of the businesses operating in those buildings.
Right, because it doesn't know why the lights are bright.
Exactly. So this static feature fusion pipeline, it breaks the moment a city deviates from the training data's average.
So it basically hallucinates conclusions because it can't adapt to unseen cities.
Yeah. And the solution to a broken blender is to, well, stop blending the ingredients.
Makes sense.
This is where the UrbanAgent framework comes in. It steps away from that single monolithic AI brain, and instead it creates a team of specialized AI agents.
Oh, that's cool. So it preserves the unique perspective of each data modality.
Exactly. You get 4 distinct agents, and each one has a very specific job.
Okay, let's run through them. So first there's the satellite agent, right?
Yeah.
Handling macro space perception.
Right. Taking in the sweeping visual landscape.
Then the text agent manages semantic abstraction. So it's actually reading and contextualizing documents.
Yep.
And the POI agent maps out the functional distribution of businesses and services.
Correct.
And finally, the 3D agent studies urban morphology.
Right, the physical shape, density, and height of the structures.
Okay, so we've got these 4 highly specialized agents.
Yes, but here's the real magic. Rather than forcing these agents to just guess based on whatever weights they learned during their pre-training, the researchers empowered them to actively acquire evidence.
Wait, yeah.
They gave these agents real-world tools.
Oh, wow. What kind of tools are we talking about?
Well, they can execute a web search, for one.
Okay.
They can also use a crop and zoom tool on satellite imagery to isolate a really specific city block.
That's amazing.
They can pull nightlight retrieval data for specific coordinates, or even use historical satellite imagery retrieval.
Oh, I see. So they could compare how a neighborhood looked in, like, 2015 versus 2020.
Exactly. This shifts the entire paradigm from static prediction to dynamic investigation.
Right.
An agent doesn't have to just guess anymore. It can go out and find verifiable data to test its own hypothesis.
Okay, but here's where it gets really interesting for me, but also a bit confusing.
Okay, sure.
Having a tool and knowing how to use it are 2 very different things.
Oh, absolutely.
Like, how does an AI agent even know when to use a crop and zoom tool versus, say, searching the web?
That is the core question. And the paper addresses this through a really fascinating 2-stage process called Tool-Augmented Agentic Learning.
Tool-Augmented Agentic Learning. Got it.
Yeah. And they build on a specific foundation model for this called Qwen3VL7B.
Okay. Qwen3VL7B.
The VL in that stands for vision language, which means the underlying architecture is natively capable of processing both text and visual information simultaneously.
Right, which I guess is an absolute prerequisite if you have an agent that needs to look at a map and read a tool manual at the same time.
Exactly. So we have a model that can see and read. Now, stage 1 of the training has to be teaching it the basic syntax of the tools.
Right, because left to its own devices, a language model just wants to chat in plain English.
Yeah, but a tool API needs specific code.
Right.
They call this stage supervised fine-tuning, or SFT. Think of it as a cold start.
Okay.
The researchers feed the model thousands of human-annotated examples, demonstrating exactly how to format a tool request in strict JSON formatting.
Oh, so the AI basically learns the grammar of the tools.
Yes. It learns that if it misses a bracket, the API call fails. It learns how to hold the hammer, so to speak.
Okay, but that just means it won't crash the program with a syntax error. It doesn't really teach the strategy of when to swing the hammer. Like, if I see a weird building, do I zoom in? Or do I check historical data?
Exactly, and strategy is handled in the second stage, reinforcement learning.
Ah,
They use a highly specific technique here called Group Relative Policy Optimization, or GRPO.
GRPO. How's that different from normal reinforcement learning?
Well, standard reinforcement learning might just give an AI an absolute positive or negative score based on whether its final answer is right or wrong.
Right.
But GRPO is much more sophisticated because it evaluates the process, not just the destination.
Okay, I want to break down how this group relative scoring actually works here, because that sounds really important.
It is. So the system gives the AI a complex urban problem and lets it try multiple different trajectories simultaneously.
Okay, like parallel processing.
Yes. One version of the agent might immediately search the web. Another might decide to zoom in on the satellite image. Another might pull historical data.
Right.
The GRPO method then rates these multiple attempts relative to each other.
So it's basically comparing the homework of 5 different clones.
Yeah.
And rewarding the most efficient path, rather than just grading against some absolute rubric.
Exactly. And the reward system is highly composite. The AI gets rewarded for accuracy, obviously, but critically, it gets heavily penalized for inappropriate or illogical tool use.
Oh, interesting. So if the text agent, which only processes documents, suddenly tries to invoke the crop and zoom image tool,
The system penalizes that trajectory.
right, because that makes no sense. Or if an agent just loops a web search endlessly without actually synthesizing the data, its relative score just tanks.
Exactly. Through this group relative scoring, the agents learn a behavior pattern. They learn to pause, recognize uncertainty, select the appropriate tool to gather external evidence, and then update their internal hypothesis before moving forward.
Okay, let's picture this in action so it's super clear for you listening. Say the satellite agent is looking at a massive, flat, green square in the middle of a density.
Okay, good example.
Initially, just based on the pixels, it assumes it's a public park. Right. And under the old Blender system, it would output park, and that would be mashed into the final guess.
But with tool-augmented learning, the agent might recognize its confidence is only moderate, maybe because the surrounding buildings are entirely industrial?
Yes, so it pauses. It triggers the historical satellite imagery tool, pulling the map from 5 years ago.
Oh, and it sees that in 2020, this exact green square was actually an active open-pit landfill.
Exactly. Then, recognizing that change, it triggers the web search tool, querying the coordinates, and discovering municipal records indicating the landfill was capped and seeded with grass.
Right, but it's still zoned as a hazardous waste management site, not a public park.
Precisely. The agent independently corrected its own visual hallucination before it ever submitted a final answer.
That is a massive leap in reasoning.
It really is.
But wait, we still have 4 independent agents operating in silos at this point. Even with tools, they are inevitably going to arrive at different conclusions about the exact same city block.
And that brings us to the second major stage of the urban agent framework. It's called multi-agent collaborative reasoning. The researchers basically place these 4 tool-wielding agents into a structured interaction graph.
An interaction graph.
Yeah, it forces them to communicate with each other and reach an evidence-based consensus.
Like a multi-agent debate club.
Exactly like that. And the agents interact through 3 specific types of connections, or what the paper calls edges.
Okay, let's go through the edges. The first one is the corroboration edge, right? That one seems pretty straightforward.
Yeah, it's about agreement. If the text agent pulls zoning data that says financial district day,
Yeah.
and the POI agent pulls a list of 20 banks and 3 stock brokerages, their predictions are mathematically aligned.
Right. They fall within a predefined threshold of agreement.
Exactly. When the corroboration edge connects them, they mutually reinforce each other's confidence scores.
Okay, so they present a unified, heavily evidenced front to the rest of the system.
Right.
But, cities are messy. So what does this all mean when they fight, like when they completely disagree?
That's where it gets fun. In a traditional model, an industrial zone and a park just average out into a weird gray area.
Right.
But this framework forces them to stop and argue.
But how does code actually argue?
It happens through the second connection, the rectification edge. This explicitly models conflict-aware correction.
Conflict-aware correction.
Yeah. The system constantly monitors the semantic distance between the agent's predictions.
Okay.
So if the satellite agent is highly confident it's looking at a park, but the POI agent is highly confident it's an industrial logistics hub, they cross what's called a rectification threshold.
The system detects a severe misalignment.
Yes.
It essentially rings a bell and forces them into a room together.
In code terms, it literally forces them to swap their evidence arrays.
Oh, wow.
The POI agent passes its retrieved JSON file of business licenses and truck depot coordinates directly to the satellite agent.
And the satellite agent, since it's running on that vision language model, it now has to process hard text data alongside its visual image.
Exactly. It forces a recalculation of its internal probability distribution.
That's brilliant.
Right.
It has to look at the trees again, but this time with the inescapable knowledge that a trucking company is registered right underneath them.
Yes. And it realizes those aren't park trees. They are heavily landscaped buffers around a corporate manufacturing campus.
Wow.
The rectification edge forces the isolated agents to synthesize conflicting evidence and actively update their priors.
Rather than sweeping the error under the rug.
Exactly.
Okay, so that covers situations where both agents are confident, but one is clearly wrong. But what if one agent is just hopelessly confused?
That happens too.
Say the text agent is reading a really contradictory municipal document and its confidence score drops to like a point 0.2 out of 1.
Right.
But the 3D agent has perfect topographical LiDAR data of the block
Oh,
and has
wow.
a confidence score of point 0.9.
That asymmetry in confidence triggers the third connection, the supervisory edge.
Okay, so it's analogous to teacher forcing knowledge distillation, right? Like an airline pilot and a flight attendant trying to diagnose a strange noise in the cabin.
That's a great way to think about it.
If the noise is coming from the engine,
Hmm.
the pilot's mechanical knowledge gives him a confidence score of point 0.9, while the attendant might be at a point 0.2.
Right.
So the system dynamically creates a hierarchy where the pilot's data overrides and actively tutors the attendant's data.
Exactly. The paper formalizes this directed relationship mathematically. The high-confidence agent acts as a supervisor, guiding the other.
Right.
Its heavily weighted evidence pulls the uncertain agent toward the correct evidence-based conclusion.
That makes total sense.
It dynamically shifts multimodal fusion from a static equation into a structured hierarchy of reasoning, all based on actual confidence metrics.
Man, we have really moved from a flawed deep learning smoothie to a team of autonomous agents with real-world tools debating and supervising each other.
It's a huge leap.
The architecture is honestly beautiful on paper. But I have to ask, does this elaborate debate club actually move the needle on real-world urban profiling?
It does. The empirical studies run by the researchers across global urban datasets show remarkable results.
Really?
Yeah. They tested the system's ability to estimate those three incredibly difficult metrics we mentioned at the start: carbon emissions, GDP, and population.
And looking at the hard numbers from the source, UrbanAgent outperformed existing deep learning baselines and even other multi-agent baselines by an average of 8.1% on the R-squared metric.
Which is huge.
Yeah, an 8.1% jump in a field where you are trying to predict the messy, chaotic reality of human economic activity. That is massive.
The raw score is impressive, for sure, but the real breakthrough is where that performance boost manifests.
Okay.
The true superpower of UrbanAgent is its strong generalization performance in unseen city settings.
Oh, right. So you can train it on Tokyo and Seattle and then drop it into Mumbai or Lego cities it's literally never encountered and it still works.
Yes, because the correlation-driven models we discussed earlier, they fall apart in unseen cities.
Right, because the superficial rules they memorize don't apply uniformly across the globe.
Exactly. A skyscraper in New York indicates a very different underlying economic structure than a newly built high-rise in a rapidly developing urban center.
The old model just sees a tall building and blindly stamps high GDP on the map.
But UrbanAgent pauses. It recognizes it's in a new context.
Oh, I see.
It retrieves historical satellite data to see how fast the building went up. It searches the local web for zoning context. It forces the 3D agent and the text agent to debate their findings.
It adapts by actually verifying uncertain inferences with external knowledge.
Exactly. The framework moves urban AI from simple pattern matching to actual verifiable semantic reasoning.
Tying this all back to you listening right now. If your job involves managing a city's carbon footprint or tracking economic growth or, estimating population density for a new transit line,
Yeah.
or if you simply want artificial intelligence to actually understand the physical world rather than just hallucinating guesses, this changes the game.
It really does.
We're finally developing AI capable of handling the contradictory reality of human cities.
It fundamentally replaces blind statistical correlation with grounded, evidence-driven profiling.
So to briefly recap the journey of today's deep dive, we started with the old paradigm, the deep learning blender that basically mashed text, images, and data into a single, often hallucinated guess based on really brittle correlations.
Right, and then we explored the solution introduced in the KDD 2026 paper, UrbanAgent.
Which is a framework that separates the data streams into specialized AI agents, utilizing vision language foundation models trained via group relative policy optimization to actively wield real-world tools.
Exactly. And we unpack the multi-agent interaction graph, where these agents are placed into a structured environment to collaborate, debate conflicting evidence, and supervise each other.
All based on dynamically calculated confidence levels, resulting in highly accurate, context-aware urban profiling.
The philosophical implication of this architecture is actually pretty profound.
Oh, yeah.
Yeah. The researchers have successfully trained a complex AI system to perfectly resolve its own conflicting viewpoints.
Right.
By forcing the system to pause, acquire new external evidence, and structure a debate based purely on verifiable corroboration and confidence. It raises a really important question for all of us.
What's that?
Is this AI just profiling our cities, or is it providing a blueprint for how human city planners and humans in general might better resolve our own complex disagreements in a world drowning in information overload?
Oh, wow. Now that is a provocative thought to leave you with. When you look at a neatly shaded map of your city tomorrow, remember just how much messy debate, evidence gathering, and course correction it takes to actually understand the streets you're walking on. Thank you for joining us on this deep dive. Keep learning, keep questioning the world around you, and we'll catch you next time.